Hi, this is Mohamedul Islam. Today in this video, I will discuss about a SAS procedure, PROC life test, which is widely used for survival data analysis. So with this procedure, I will show you how you can compute survival estimates and how you can plot the survival curve using Kaplan Meier method. And then I will also show you how you can perform comparison test of survival distribution between treatments. And then I will also show you how you can perform test of association between survival times and covariates. Lastly, I will show you how you can export all of your estimates to a dataset. So let's get started.
Suppose, think about a scenario where a researcher or a sponsor think that his newly developed drug that can expand the lifetime of last stage cancer patients. And as the cancer is at the last stage, the patients are more likely to die. And here the event of our interest is basically death. And the researcher conduct a placebo-controlled parallel study and counted the time in days from date of exposure to death, and there might have some subjects they lost to follow up, or they withdrawn from the study, or somehow the actual time to death is unknown. So there might have some censored observations. So here, let's see with the data set, the data set we get from the trial. So this is the data set, which is Adam time to event data set, and this is the subject ID, where we have 1 to 30 subjects, and in the param variable we have which indicates basically the events. So here basically the event of our interest is death. So here in param variable we have only one value label, which is death. And in treatment there are drug A and placebo. As this is a placebo control parallel study, we have seen, so there would be a group of subject, they will receive placebo treatment, and another group of subject they will receive the drug A, the trial drug. So this is our treatment drug A and placebo, and this is the numeric form, and this is our main variable of interest, which is named here as ABL as per CDISC standard, and it is nothing but the survival time of patients from date of exposure to death in days. So this is the survival time variable, and this is the sensor variables, which basically indicates whether it is a censored observation or it's an event. So 1 indicates it's a censored observation, and 0 indicates it's an event. And this is the age of our subject, and this is the age group. So here we basically splitted our subject into two age group. One is greater than 50 and another one is less than 50. And this is the numeric form of age group. Basically we rank them. The lower age group have the lower rank, and as the age group becomes higher, the numeric form is become increase. For subject who have age less than 50, their numeric form is 1. We ordered them, and the age, the subject whose age group is greater than 50, his uh, numeric form is 2. So this is the order of our age group, and this is the uh, gender of our subject, if for female and for male, as per CDISC standard, and this is the numeric form of sex. So now let's get started with a simple PROC life test procedure. So let's see what it produces. So our procedure is start with PROC life test statement, and here after writing PROC life test statement we need to specify the input data set here, which is ADTTE, Adam time to event data set, and the key requirement to perform the PROC life test procedure is time statement. So here in time statement we need to specify the survival time variable, which is ABL, and with an star symbol, we also need to specify the censored observations. So in C and SR variable, we reference our censored observation by 1, and here we listed the 1 as it is the censored observation. And now let's run it and see what it's basically produce, what's the output is. So we have run the code and everything is fine in the log, and this is the output we get from the simple proc life test program. So basically what it gives us, so we get the product limit survival estimates. And this is the product limit survival estimates of our dataset, and basically the analysis we get here based on all of the observations. So this is the time eval, time survival time we have in our data sets, and they basically forcefully impute one time which is 0, and when time is 0, the survival probability is always 1. And so this is here basically in this column, this is the survival probability at each of this time point. uh, so this is the survival probability, and here is star. It means there is, at that time there was a censored observations, uh, and this is the probability of failure, and this is the survival standard error, and this is the number failed uh, at each of this time point, number of events occurred, and this is the information number of subject at risk at these time points. So this is the product limit estimates, or you can say the Kaplan Meier estimates we get from the simple PROC life test program, and it also gives us the point estimates, the quartiles point estimates. So here we can see the 25% the first quartiles point estimates, second quartile and third quartiles, and these are the value of point estimate. And this is the, they also gives us the confidence interval. So, and here they basically use the log-log transform method to compute the confidence interval. So it can be customized, you can specify any other transform method to get your confidence interval at these quartiles, at these percentiles. So, and this is the mean information we have, the mean survival time for all of the observation here is basically 94.979. This is the standard error, and this is the uh, survival curve, or you can say Kaplan Meier curve. And here basically the tick mark we are seeing in this graph, these are basically indicating there are the censored observations. And lastly, we also get a censored summary, summary of uncensored and uncensored values. So here in our data set, total number of observations or subjects basically 13, 19 meet the events, and 11 was censored observations. So this is what we get from the simple PROC life test program. But however, this is not the output of our interest. Basically, we want to compute uh, product limit estimates and all other analysis separately for each of the, treatments. So how can we do that? Let's see. So in order to get uh, all the analyses that we have seen in uh, in the output. So, separately for each of the treatment, you need to specify another statement strata, and we need to specify the treatment variable by which we want to compute the product limit estimates and all other summary information. So, and when you basically specify the strata statement, then it will also perform the comparison test of survival distribution between the treatments. So here we are going to get all of the analysis separately for each of the treatment, and we also get the comparison test results. uh, and here we can specify the method. So here the method is Kaplan Meier method. So we can also reference here product limit method. Both are exactly the same thing. So this is the method, and we can also specify the confidence interval computation, the transform method to compute the confidence intervals. So here to do that, you need to write the conf type statement, and here we will specify the type, the transform method on which we want to get our confidence interval for the point estimates, quartiles point estimates. So now let's specify it as in square root. So there are several transform method to get your confidence uh, interval, to compute your confidence interval. Those are like S in square root and logit, linear. These are some methods available in PROC LifeTest. So here basically we use this method to get the confidence interval, uh, and in order to plot the Kaplan Meier curve, it's better to we have to specify the plot statement, and here within the plot statement we need to specify S. So S will basically create the Kaplan Meier curve, and when we are trying to plot something, it's good practice to enable the ODS graphics option. So we are enabling the graphics options in the beginning of the program, and at the end of the program we are again uh, disabling it. Uh, so now let's run it at see and see what our result is. So this is our result we get from the program. So now we get the product limit estimates basically separately for each of our treatment. So this is the product limit estimate for drug A, and here is the quartiles informations we get separately for drug A, and this is the mean uh, survival time for the patients treated with drug A. And similarly here for we get analysis separately for placebo treated patients. So in stratum 2, the analysis is the result we get here from placebo treated patient. This is the product limit estimates, and these are the quartiles point estimates of patients treated with placebo. This is the mean survival time of patients treated with placebo. So here we can see one thing, that it's clearly visible that the subjects who treated with placebo, their mean survival time is basically significantly lower, almost half than the patients treated with drug A. So it's basically almost telling that there is significant difference in mean, and basically the patients treated with drug A, they have basically higher survival time. And however, this is the summary of censored and uncensored observations, and for each of our stratum, each of our treatment, like drug A, there are total 19 records, 11 meet the event and 8 was censored, and for placebo treated patients there was 11 records and 8 meet the event and 3 was censored records, and this is the total information, summary information, and this is basically the result of our comparison test. Now let's see what basically the comparison of survival distribution test is telling us. So this is the p-value from log rank test, and this is from Wilcoxon test, and this is the p-value from likelihood ratio test. However, see the p-value here is significantly low, which it's basically less than 0.05. So as by default, all test is performed at 5% level of significance. So we will compare the p-value with 0.05 to conclude the decision. So here we can see the p-value is less than 0.05, which is telling that there is difference between survival distribution of drug A and placebo. And Wilcoxon test result is also telling the same thing, but the likelihood ratio test result is telling that different thing. It's telling exactly the opposite thing, that there is no difference between the survival distribution of drug A and the survival distribution of placebo. So this basically the result here is basically there is something mismatch, or they are basically telling something different thing. So we will see that which test will appropriate. However, now let's move to the Kaplan Meier curve. This is basically an overlay plot where in same set of axes we get the Kaplan Meier curve, the survival curve for drug A. The blue one represents the survival curve for drug A, and the red one is for placebo uh, treated patients. So here in survival curve, or the Kaplan-Meier curve, we can clearly see that it's almost clearly visible that patients treated with drug A, their survival time is longer than patients treated with placebo. So now let's create another plot that can helps us to make the decision whether the likelihood ratio test is appropriate or not. So let's run it and see how what the log uh, survival log negative log of survival probability versus time plot is telling us. So this is basically what we plot, negative log of survival probability versus time plot. So here in the plot we can see that the the line we have, these are not straight line, these are curved line. So when it is not a straight line, then we can assume one thing, that our survival time is not following the exponential distribution. So here the likelihood ratio test, basically it's a parametric test, and whenever you are trying to perform any parametric test, you must have to meet the assumption, and once you can meet the assumption, your parametric test will be the appropriate. So here for this likelihood ratio test, we the assumption we have to meet that our survival time has to be follow the uh, exponential distribution. But however, from the negative log survival probability versus time plot, we can assume one thing, that our survival time is not following the exponential distribution, as the curve we get from this graph, it's not in a straight line. So here basically our likelihood ratio test is not appropriate for this data set. So now let's plot another plot, which is log of negative log survival probability versus log of survival time. So let's plot it and see how it can help us. So we are plotting that curve. So here we get the plot, uh, log of negative log survival probability versus log of survival time, or log of eval, which is nothing but the survival time. So here basically the line we are seeing here, those are likely parallel, and when these kinds of plots lines are likely parallel, it basically indicates that the log rank test is much more powerful, or much more appropriate than any other test. So here the log rank test, basically it's much more appropriate than any other test for comparison test, for comparison of survival distributions. The log rank test, basically here it's much more uh, reliable. So now we want to see here in our graph, this is our Kaplan Meier curve. So here basically we want to see the p-value of our comparison test. So how we can see that, how we can show it in the graph. So in order to show the p-value in your Kaplan Meier curve, you just need to write a test statement here, and you will see the p-value, the comparison test p-value in your Kaplan Meier curve. See here we can see the p-value of log-rank test, p-value of comparison of this survival distribution of drug A and placebo. Now we also want to see the number of subjects at risk at this time interval. So how can we show that in the Kaplan Meier curve? So in order to do that, we need to write another statement at risk, and we need to specify with an equal sign, we need to specify the time interval on which we want to show, on which we want to see the number of subjects at risk. So we want to see at this interval 0 to 125 by 25. So in this interval we want to see the number of subjects at risk at our Kaplan Meier curve. So let's run it and see how it looks like. Everything is fine in the log, and see, now we can see the number of subjects at risk at this at our specified time interval. So now if here basically we get our Kaplan Meier curve survival plot in an overlay plot. I mean, in the same set of axes we are getting the multiple plot basically. So if we want to get our Kaplan Meier curve separately, and then how can we do that? So in order to get the Kaplan Meier plot the Kaplan Meier curve separately for each of the treatment, then you need to specify here the strata statement, and with an equal sign you need to specify the panel. So once we write it and run it, now we can see the Kaplan Meier curve separately for each of our treatment. Now we want to see basically the confidence band in our curve. So in order to do that, here you need to write another statement, CB, which is stand for confidence band, and here we need to specify the method. So we basically want to see the whole Wellner confidence band in our Kaplan Meier curve. So here you need to specify CB equal to HW, which is where HW stands for whole Wellner confidence band. So when we run it, and we will going to see the confidence bands in our survival curve or the Kaplan Meier curve. So here, see, you can see the confidence bands in our curve. So however, that's all in part A. So in the next video I will show you how you can perform test of association of between survival time and covariates, and how you can export all of your estimates to a dataset.